Okay, we're going to be working on an activity today titled Distracted Driving. This is going to be a great introduction into statistical analysis through simulations, okay, helping us kind of figure out whether we feel like we have convincing evidence of something that occurred maybe in real life, or whether there's not convincing evidence of an explanatory variable causing a response variable. So here's where we want to start. In statistics, for a significance test, if something is occurring less than 5% of the time just by random chance, it is considered to be very unlikely to occur in real life. Okay, so 5% is our benchmark, and I know that we've talked about that before. But when you get finished with an experiment, your goal would be to maybe be able to conclude that your explanatory variable is what's causing the change in your response variable. Like that's what you'd like to be able to say, but we aren't necessarily always able to say that. When you can say that the explanatory variable is causing the change in your response variable, that's when we can say that we have convincing evidence. Okay? And it also means that your results then are considered statistically significant. Okay. The other option is there just might not be enough evidence for you to conclude that the explanatory variable is what's causing the change in the response variable, and that's when our results are not statistically significant. Now, how do we know whether we have the evidence or we don't have the evidence? Well, typically, whatever happened in your experiment, we then replicate those same conditions through a simulation. And when you perform a simulation, you are performing something where random chance is in control in terms of who gets allocated to which treatment group. And we're able to kind of see, were the treatment groups somehow lopsided and we didn't know that they were lopsided, and so all of one type of person got put in one treatment group, and so it wasn't really the explanatory variable that's causing the change in the response variable, but it was just the mere chance of when we used the hat method or the coin method or something to randomly split these people, it just happened by chance that the groups were lopsided in that way, okay? So by performing a simulation multiple times over and over again to sort of simulate your experiment, you can compare those results to the results that you got. And what we're really looking for is you've got convincing evidence that your explanatory variable caused your response variable if in your simulation, less than 5% of the time, okay? If less than 5% of the time, that's what goes in this box here, you get similar results from what you got in your experiment in your simulation when you did this just by chance, okay? Because if it's not very likely, which is what less than 5% means, that something's going to happen just by chance, and that unlikely occurrence actually occurred for you when you performed your experiment, then it's probably likely that it was really the explanatory variable that's causing the change in your response variable and not random chance of who got put in which treatment group. However, if you perform your simulation multiple times and you notice that more than 5% of the time, you're getting similar results to what you got in your experiment, and you're getting those results by chance in your simulation, then that's when you're saying, we really don't have enough convincing evidence to say that it was in fact the explanatory variable that's causing the change in the response variable, because it seems like this is happening pretty frequently just by random chance. So it's chance that's causing it to happen, not the explanatory variable causing the response variable to happen, okay? And so typically, and we'll do this in the second semester, we'll be running different statistical analysis, but since we haven't learned that, we're going to be running a simulation. So I want to look at a specific situation here. We're going to be talking about this idea here of, is talking on a cell phone while driving more distracting than talking to a passenger, okay? So this is an actual experiment that students at the University of Utah conducted. And what they did is they took 48 undergraduate students and, they did the best they could. They randomly assigned half of them, 24 of them, had to drive in a driving simulator while they were talking on a cell phone. The other half were assigned to drive in a simulator while talking to a passenger. Okay, now how they were able to measure whether the students were, or the drivers were distracted or not, is these drivers were told at a designated exit, you have to turn and get off at that exit. There's like a rest area there. Okay, so they recorded whether the students turned off at that designated exit that they were supposed to. Okay, and they were told which exit that was before the experiment started. Okay, now here's what the results are in this table. Okay, you can see the table's kind of displaying here for us a couple of things. The columns are your treatment groups. So we had, I'm going to just total here, we had 24 students assigned to a simulator where they were told to talk on a cell phone, and 24 where they were speaking with a passenger. The rows are measuring whether they actually stopped correctly at that exit where the rest area was. Okay, now you can see that there were a total of 33 out of these 48 students who did not get distracted and they stopped at the correct exit. The no row means they did not stop at the exit correctly. We had a total of 15 students who did not stop correctly at that proper designated exit. Okay? So the question is there any evidence in this table that shows that cell phones are more distracting than passengers? Well, we certainly could look at this and say, look, there were 24 in the cell phone group. 12 of them totally missed the exit. So half of the 24, half of, I'll say, the cell phone group were distracted. While how many of the passenger group were distracted? Well, only 3 out of the 24 of them. Okay. Of the passenger group were distracted. Okay. Now, keep in mind, we have not performed our simulation yet. We're just looking at the data from this initial experiment that these students at the University of Utah conducted. Okay, so it does feel like there is some evidence here that's maybe making us feel like cell phones are more distracting than passengers, but we really need to make sure that our evidence is what they would call in statistics convincing evidence. And so let's talk about what that means, and let's see if we can go ahead and simulate this here. Okay. First, what you do when you're performing a test like this is you have to make an assumption at the beginning. And so here's what our assumption is going to be, that talking on a cell phone and talking to a passenger are both equally distracting. Okay? Now, I know that we're suggesting that the evidence in this table is not showing that that's the case, but that is what our assumption is going to be here at the beginning, that it is equally distracting. Okay? So what that means is if these are both equally distracting, and you'll notice we had 15 total students between the two treatment groups who got distracted and missed the exit. Okay? So if cell phones are just as distracting as a passenger or vice versa, then those 15 students, they would have missed the exit regardless of which treatment group they're in. They're just people who easily get distracted. So whether their distractor is a passenger or a cell phone, they're probably going to miss the exit. And these 33 people, regardless of which treatment group they were in, they're not going to get distracted. This is all under the assumption that cell phones and passengers are equally distracting to a driver. Okay, so our null hypothesis, as they would refer to it in a science class, and as we will refer to it later in the second semester, is that talking on a cell phone and talking to a passenger are equally distracting. Okay, and so we're going to run our simulation under the assumption that that is actually true. Okay, and we're going to see if the evidence shows something different. Okay, so we want to see, well, what's going to happen if the results are completely left up to chance? So we're going to have 48 people, 15 who knowingly are easily distracted. What is the likelihood that 12 of those 15 people, through just random assignment of treatment groups, would have gotten placed all in the cell phone group. Like, it does feel a little imbalanced here that 12 of the 15 got thrown into the cell phone group. Okay, so we're going to simulate this with a deck of cards here, okay? And what we'll be doing in class is you're going to be given 48 cards, okay, because there were 48 students in the experiment. 33 of the cards are going to be number cards. Okay, this is just from a deck of cards here, and that represents the individuals who actually stopped correctly at their exit. Okay. The 15 people who missed the exit, the people who are easily distracted, those are going to be represented by any face cards or ace cards in the deck. And so the 33 plus 15 gives us a total of 48 cards. So everyone's going to be given 48 cards, okay? And you're going to be asked to mix them up and really shuffle very, very well. And shuffling is going to represent that, the outcomes are not affected by the treatment. So everything's going to be done here randomly. And we're going to have two little sticky notes, I guess, on your desk. Okay, one sticky note is going to be labeled cell phone for the cell phone treatment group here, those that were distracted by a cell phone. And the other one will be labeled as passenger. Okay, you're going to just back and forth, put cards in a stack, back and forth between the two groups. We've already shuffled, so they've been randomly assigned there. And you're going to have 24 cards in the cell phone pile, and then 24 cards are going to go in the passenger pile. Okay? What we are interested in is we're interested in this cell phone pile, how many of those 15 easily distracted drivers got placed by random chance in that cell phone group. Okay, so you would pick up that stack from the cell phone group and you would count how many face or ace cards were in there, because our faces and our aces are those drivers who are easily distracted and they missed the exit. Okay, now this is what our results were in class. You can see that this simulation was performed 40 times. Okay, I had every student kind of do this 3 times, and I just added some in here as well. Okay, and you'll notice here's where our dots kind of landed. Okay, so when we make our conclusion, here's what we want to look for. Remember, in the original experiment, 12 of the 24 drivers who were using the cell phone missed the exit. Okay, that's what happened in the original experiment. But based on our class simulation, we want to find out what's the probability that 12 or more of the cell phone users missed the exit, given that the cell phone users are equally distracted as talking to a passenger. So I'm going to look at the dot plot, and I want to see how many dots fell where we had 12 or more people in the cell phone group who missed the exit. And you can see that only happened one time out of these 40 simulations. Okay, 1 out of 40. So I'm going to go ahead and divide 1 by 40 so I can see what my percentage is. That comes out to about 2.5% of the time, through random chance, am I looking at 12 of those 15 distracted drivers randomly being placed into the cell phone group. So if this probability is very low, and very low means under 5%, then that means that it is unlikely that this would have happened by random chance alone. So our assumption that cell phone distracting and talking to a passenger being your distractor being equal is probably wrong, okay? And it probably, what we're seeing occurring, that there's a lot more people in that cell phone group who miss the exit, is probably due to cell phones actually being more distracting than passengers, okay, which means the results would be statistically significant. Now, had we looked at our simulation and there were a lot of our dots were landing over here where there were 12 or more of those 15 distracted drivers falling in the cell phone group, then we probably would have had that percentage being reasonably high, meaning it was greater than 5%, saying, you know what, this is something that could easily have happened just by chance. We just simulated it 40 times. It happened more than 5% of the time when we simulated it 40 times. So maybe cell phones aren't more distracting, but this is just something that easily could happen by chance, that you get 12 or more of those 15 distracted drivers thrown into the cell phone group. Okay, we know that for this, we're falling into this situation. So how we would draw our conclusion is, since the simulation yielded that 2.5% of the time, which is less than 5%, 12 or more distracted drivers would land in the cell phone group just by chance, that's when we say we actually have then convincing evidence that talking on a cell phone is in fact more distracting than talking to a passenger. These results then would be considered to be statistically significant. There's a lot we're going to be doing in the future that revolve around this idea of simulation and looking at whether your results fall above or below that 5% mark to kind of dictate whether you have convincing evidence or not. I think the key here is we want to make sure that when you're looking at your results from your simulation, if something that you're looking at is only happening less than 5% of the time, that's when you've got the evidence in support of the explanatory variable causing the response variable. It's when what you're looking at happens frequently, more than 5% of the time, randomly, that you don't have the evidence in